There are many videos you can find online about free energy, and I am making a video to suggest that free energy does not exist. Most free energy wizardry are based upon three basic principles: high voltage discharge, electric magnetic field, and heat pump. I will be demonstrating all of these three categories in this video. Starting off with this little Tesla coil, in which produces high voltage plasma. And I will just plug it in here. It acts the same way as flame or spark discharge, and is a very hot overheated air essentially. So at the top of the coil, it's trying to push current here. Let's see. Yeah, focus. It's trying to push current into the air, and it's like ionizing the air, superheating it, and making it glow. And I can demonstrate it by putting a CFL around it. Unfortunately, I don't have my gas discharge lamps. Some people may say if Nikola Tesla has won the war of current instead of Thomas Edison, we would be able to have free energy, but that's absolutely inaccurate because this is essentially a very inefficient and invalid way of transferring energy. It's not storing it or reusing it in any real form. As you can see here, the gas discharge lamp, and if I put it close to the Tesla coil, it glows. And it's a very interesting effect here. Absolutely no wizardry here. Okay. Just to explain further, this circuit in which produces the high voltage, it's also based upon electromagnetic field, in which is a way of transferring energy. There is absolutely no physical connection between the coil and the energizing primary winding. All the current is transferred through air essentially, and this is what the second part of the video is going to be. I have created this experiment setup yesterday, and essentially what it is, it's switching step-up voltage right here into a high-frequency alternating current. And as an alternating current passes through a conductor, in which is right here, the coil, it induces a magnetic field. And if another conductor cuts into that magnetic field, it's going to induce voltage. And if we hide everything under a piece of paper and we grab a piece of receiving coil, in which I'll explain further, and put it down there and turn it on, as you can see, free energy, but obviously that's not the case here. It can actually get really bright if it's closer and not if it's further away. And for this piece of coil, it essentially is a printed circuit board, or PCB, with very thin wires etched into it. In order to make everything easier to understand, here is literally just loose wire wound into a coil. And if we turn it on and attach an LED to it, the LED will glow. It doesn't. It does. It's just not very bright, because the more the winding, the higher the voltage is gonna be. Let's see. There are many other ways to increase efficiency, and one of which is to add a core material inside of the windings. And this is essentially how every single high-frequency transformer works. This is a standard transformer used in almost all switching power supplies. And in the middle, it's just copper wire wound on a spool. And on the outside, there are magnetic core materials, in which, in this case, it's ferrite. And ferrite is just a special type of iron, I guess. This is a same transformer, just teared down to the bare minimum for further explanation. And as you can see, it's got only the primary winding, and if we fit the core material on each side of it, it becomes a transformer. But it needs another winding, of course. Here I have a LCR meter to further explain electromagnetism. What it does is it analyzes the properties of a component, essentially. And right now it's hooked up only to a piece of wire, as you can see here. It's just wire, nothing too special going on. And right now the reading is 614 milliohm, which is a resistance. It has very minimum inductance property. However, if I wind those coils together, to form a coil out of this piece of loose wire, that's gonna be hard. Okay, here. We can observe a very low inductance value on it, although it's only, come on. It's only, it's got a bad connection. Okay. It's only around 3 microhenries, which is a very small amount of electromagnetic force, but it still is something. What that suggests is that whenever there is current flowing into the wire, it creates a magnetic field around it, and it goes like this. It's like 2 rings around it. And whenever the current is removed, that magnetic field gets induced back into the coil and produces electricity. Here, a better way of understanding it, here we see that transformer we had a minute ago. We remove the core material, and we hook up the meter to see what it is like. Right now it's acting very much just like a straight wire, because it's just wire wound on a spool. And the reading is only 1 microhenry, which is extremely low as well. However, if we install the core material like this, the inductance will skyrocket up to very, very high value. Not really, but it has become like 9 microhenries, which is like quite a lot higher. And if I remove a half of it, it drops down a little bit. And if we remove everything, nah. The same working principle applies to this piece of coil. As you can see, the readout is at 450 microhenry, which is a lot higher. That's because there is a lot of turns on this board. And it's acting just like a receiver coil, or like the secondary winding on a transformer, except that the core material is air, which is a lot less efficient compared to ferrite or iron powder. It still works, and that's why we have wireless energy transfer devices such as phone chargers, wireless phone chargers. This is a piece of DIY junk, and if you plug it in, it provides current in the coil, which is backed by a magnetic material, which increases its inductance for higher transfer rate. To better explain the working principle of transferring energy with a changing magnetic field, we can use the oscilloscope with a loop, a pickup coil, to measure the voltage induced by having a conductive material cutting into a magnetic field. As we turn it on and we move the probe close, we can observe the high frequency switching pattern of the magnetic field. And if we move the LED and the probe at the same time, we can see that the waveform is proportional to the brightness of the LED. It's probably really not very easy to say. Okay, let's turn up the intensity here. Closer means more amplitude, and away means less amplitude. As you can probably observe that whenever the LED is cutting into the magnetic field, the the amplitude observed on the oscilloscope decreases. That also suggests that free energy does not exist, because the more energy that's converted into light on the LED, the less energy would be able to make its way into the oscilloscope. Lastly, I explained the working principle of a heat pump and how it produces energy, in which does not come for free. Here on my hand is a filter cooler plate, in which are usually used in many refrigerators or whatnot. If we provide a current into it, it's gonna get cooler on one side and hotter on the other side. However, it's not producing heat or producing coldness. All it does is that it's pumping heat from one side of the plate to the other at a relatively low efficiency, maybe at around like 20%. These plates are also used to produce that kind of a little fan that is set on top of ovens and just rotates on itself without being powered. But it's not wizardry or magic. We can measure the current or voltage produced by it with a multimeter. However, I already tried. I wish I would be able to power an LED with it, but it's just not powerful enough. Alright, so here's the plate, and the side with the text is a cold side, so we touch it to the heatsink, and if we just somehow plug it into the multimeter and I'll warm it one side up with my hand, as you can see, a voltage is induced, but it's extremely low. It's 0.09. I've already successfully made it to like 0.3 for a second, but that's not very high. Another way we can heat it up is with a soldering iron, because why not? And as you can see, it's gonna go up to like 200, 300 degrees Celsius. And we just heat it with a soldering iron. And as you can see, the voltage did rise up higher. However, it's just insufficient to do pretty much anything. Unless it's set on top of an oven or a furnace, it's not gonna be able to produce enough energy to power anything. In fact, this technology has been used in some factories to recycle the energy lost in chimneys. So, yeah. And inside of those plates are bimetal junctions, which are essentially two different types of metals joined together. That's it. And when a heat is applied, the electron activity of different metals will rise differently, and the differential between the two metals will end up being a voltage, as it is displayed here. And this reaction kind of is also reversible. So if you put in voltage, it pumps heat, and if you allow heat to travel through, it provides voltage. Some may say, like, if you just leave it in a hot summer day, they're gonna produce voltage. That's not the truth, because energy happens when there is a change, there is a difference, there is a movement, and if the entire surrounding temperature is just warm or hot, it's not going to have a flow or a motive force, and it's not going to be able to produce any voltage or energy. Now the filter cooler is powered on, and the cup right now is being chilled at the top load, at the thermal load, and the heatsink is becoming warmer. And right now, around 5.8 volt is being put into the cooler. If I turn off the power supply, you'll see that the voltage does not drop to zero. Instead, it stays at around 1 volt for a very brief moment. That is when the temperature differential was resetting back to its original state, and that's releasing energy. With science instead of wizardry, you can make a desktop drink chiller that can reach a temperature differential of around 30 degrees Celsius.